This video will introduce the topic of graphing and solving linear systems. The learning outcomes will be to name the type of linear system, state the number of solutions the system may have, state the solution sets, and to describe the graph of the system. We will also cover solving linear systems by graphing, solving linear systems by substitution, and solving linear systems by elimination. Previously, we discussed that when solving a one-variable equation, we could have three possibilities, either a contradiction, a conditional solution, or the identity. The same is true for a system of equations. So let's talk about sorting all this information in a chart. You can find this table as one of the pages in the My Notes for this homework. When we're graphing a system of equations, there's three things that can happen in terms of our graph. We can either have parallel lines or intersecting lines. Notice I didn't put these to be perpendicular. Perpendicular would give me intersecting lines, but they don't have to be perpendicular. And then the last thing is the same line scenario. So what happens is that when we have parallel lines, we have zero solutions because there are no points that they have in common. When we have intersecting lines, they have one point in common, which means we only have one solution for that type of system. And if we have the same line, every single one of these points is a solution, so we actually have infinite many solutions. The solution set for zero solutions would be the empty set. So we use the null space to indicate no solution. If we have one answer, it will be in the form of the point, whatever number for the x value, some number for the y value. Notice that our point will be in curly brackets, as the curly bracket represents the solution set. And then the last one, when we have infinite many, I'm going to put a little asterisk here, and because it may fit or may not fit, so you might want to put it at the bottom of that page. And what happens, we have two choices. We actually call that arbitrary. So what does that mean? You have two choices. One would be that you let x be some arbitrary number, and then you're going to have your y value would be some f of x function. Or we can have the opposite. We can have a y value for our point and then have a f of y for my x value. So either way, it's still going to be a point, an x value and a y value in parentheses and inside our curly bracket. This first one that I showed you is actually what we call x is arbitrary. And then the other one is called y is arbitrary. So we want to pay close attention to how they want us to write our answers, either in x arbitrary or y arbitrary. When we talk about a name of the system, remember we had different ways of writing it for one variable. When we had a contradiction, that's when we had no solution. So in our case, we would actually call this an inconsistent system. If you do have one solution, we call it consistent. That just means you have a solution if it is a consistent system. So this one over here is also a consistent system because we did have a solution. However, since we only had one, we call this a consistent and independent solution. Whereas this one has a whole bunch of them, and we find that one of the values is dependent on the other, we call this a consistent and dependent system. So those are going to be our new names instead of contradiction, conditional, and identity. So big thing to remember is that when you have parallel lines, those slopes will be the same. So they're going to have the same slope. The two lines will have the same slope, but they will have different y-intercepts. If you have intersecting lines, you have different slopes. The y-intercept could be the same. They don't have to be. And if you have the same line, then they have the same everything. They have the same slope as well as having the same y-intercept. That's why you end up with the same line. So that's what happens when you're graphing. Now algebraically, because you will be asked to solve this linear systems by graphing as well as by algebra using substitution or elimination, algebraically what happens as you're coming along solving for the no solution one, you're going to get something that's inconsistent with reality. Something like 0 is equal to 3. Something that is definitely not true. When you're solving a consistent and independent system, you actually solve and actually find a value for x and you find a value for y. When you have a consistent dependent system and you're solving, you're going to get 0 is equal to 0. So this is very similar to what we saw when we were solving one variable equations. Now let's go to solving linear systems by graphing. One of the very first things that I want to mention is that you can actually get nice pretty graph paper like this by clicking on the graph paper link found in my MATLAB. But you can also go to a website called MathBits and find it there. Let me show you that. On mathbits.com you can find lots of resources. I like to refer my students here for two things. One of them is going to be the calculator help, and then the other one is for graph paper. So if you click on graph paper, you're going to get a whole bunch of choices, but I like to pick this one right here that says 10 by 10 templates. Those are the best ones I find. When you do that, you end up getting the same thing that I have on the link. So you'll get 4 grids with plenty of space to write on. Alright, so back to our notes. So solving systems of equations by graphing, what we need to do is we need to make sure we know how to graph one equation, and again you can see some reference materials on my MATLAB. But if you can graph one, then you can graph 2 equations onto the same graph, and I'll show you an example of that. So we're going to graph 2 lines on the same graph paper, and what we're going to be doing is looking for either a point of intersection, parallel lines, or if it's the same line. And then we're going to place our answer in a solution set like we mentioned on that table. So let's go to another page that's on my notes. And let's do an example here about solving by graphing. So let's say we have a system of equations that says 3x plus 2y is equal to negative 4 and negative x plus y is equal to 3. So that's our system. So I'm going to separate them and write them individually. So I'm going to write my 3x plus 2y is equal to negative 4 and decide how I'm going to graph that. And I'm going to have my negative x plus y is equal to 3 and decide how to graph that. So as we can see, the one on the left is actually in standard form. So I'm going to use my intercepts and see if I can graph that. So one way is let x equal to 0. So we're going to cover this up. And then I'm going to solve for y, and I'm going to find that y is equal to a negative 2. Because I just divided both sides by 2, and that's how I got my negative 2. We can also try the other way and see if that will work for us. We can let y equal to 0, and then we're going to solve for x, and we're going to find the point 0 for y and negative 4/3 for my other point. Now this is not what we would consider a pretty point, so I'm not going to use that. I'm going to see if I can find the slope. We can use the fact that we mentioned earlier in one of our videos that the slope is negative a over b. If you have standard form, then you can use this for our slope. So we can find that our slope is going to be negative 3 over 2. So now I have a point and I have a slope, so I can use that to graph this line. The other thing I could have done is I could have rewritten this into y is equal to mx plus b form if I wanted to, and I could have found the same information that I just finished finding. And again, we could do the same thing for this other equation, so I'm going to go ahead and do that. I'm going to do this one in red so that way we can see the two equations when we graph them. So again, I'm going to let x equal to 0. When I do that, I'm going to find that y is equal to 3. And if I let y equal to 0, I'm going to find that x is equal to -3. So this one's pretty good that I can use 2 points instead of having to go find the slope. So I'm going to do that with my graph. So for our blue graph, we're going to go to the point 0, -2. That would be right here. And then I'm going to use my slope of going down 3 and to the right 2. Down 3 and to the right 2. Or go up 3 and to the left 2. So I'm going to do that one. So up 3 and to the left 2. Up 3 and to the left 2. So I'm going to continue to do this so that we can get our line, and I'm going to see if I can do this. I would probably use a ruler or something to connect those points, because we want to be as accurate as possible to see if there's going to be a point of intersection and where that point's going to be. So I'm ready to do my red line. So I go to 0, 3, that would be up here, and I go to -3, 0. And if you want to, you can see that I have to go up 1, 2, 3 and to the right 3. So I went up 3 and to the right 3. So we can see that that's going to be the same thing as 1 over 1. So we can see our slope of up 1 over 1, up 1 over 1, up 1 over 1, and we can see how we got to that second point. And I can keep doing that, and we can find our line, our red line. And I apologize for not having a beautiful straight edge or a straight line, but we can clearly see that we have a point of intersection right around here. So we're going to write down that that point of intersection is the point -2, 1, and our solution set will be that point. So what happens is if we were to plug in that x value and that y value in either as well as both of those original equations, it will be a true statement for both of them. So this point is on both lines. And that's how you solve linear systems of equations by graphing. When you want to solve linear systems by substitution, one suggestion I have is to pick one equation in which you can quickly solve for one of the variables, either x or y, it doesn't matter which one, and solve for that particular variable. So let's say, for example, you can quickly solve for x. Well, then you're going to have x is equal to some expression, and that expression is going to have y in it. Then you're going to get that expression, and everywhere you see x in the other equation, I'm going to put the expression. May I suggest that you use parentheses around the expression when you're doing substitution. This will give you a linear one variable equation to solve, and then we can just solve our equation. And that will solve for, remember we said we had the expression for x, so this way we'll be solving for the letter y. Once you do that, get your value for y and substitute it into any of the equations to solve for x. And again, you should be able to place your answer in the solution set. And you should see examples of this type of problem provided by the textbook. Same thing with solving linear systems by elimination. The video will be from the textbook, and again, it will go through those steps, but essentially what you want to do is place equations in standard form. That's going to be step number 1 all the time. Then after that, pick a variable to eliminate. You're going to multiply either one or both equations by a non-zero constant. And really what you want to do, let's say we wanted to get rid of x, then you want to make sure the coefficient, the number in front of x, for both equations is actually the same number, except one positive and one negative, so that when you add them, they will be eliminated. The x variable would be eliminated, and that would give you a one variable equation to solve for, which will involve y. And then from there you can do the same process again if you like, and just eliminate the y's. Or from here you can use substitution by putting it into one of the original equations to find the other variable. Again, you'll see videos provided by the textbook that will show this. And finally, make sure you place your answers in a solution set. There's one more additional, or maybe two more additional videos provided by the text to talk about what happens if you have a inconsistent system, as well as what happens if you have a consistent dependent system. So anyway, I leave you with that, and that ends this video.